Okay, we're going to talk now about different types of rates. Uh, and they typically fall into two different categories. One, the notion of a rate as a proportion of some whole. For example, different types of blood types in the population. What proportion of the population has type O, type A, and so on. A second type of rate is a rate of change. For example, the inflation rate or an interest rate. Rate of change typically involves time. So take a look at the first one initially. Here, I've gotten data from someplace, types of garbage, whether it's organic, paper, plastic, glass. You'll notice that proportion, I didn't put in the percentages here. You can see them here, these percentages, but you can imagine that they're there. Um, Here they are, here, these percentages. I didn't indicate them, but they add up to 100. Um, uh, this fits itself very well for um, sits itself well for what's called a pie chart. Excel does this very well, and we'll look at this in the class. Incidentally, if you have any kind of table or chart like this, I call it on the left is a table, on the right is Excel calls it a chart, I'd call it a graph. You should always indicate source like this here, but don't indicate it as a URL. You should indicate it as, for example, the actual website or the name of the website, not gobbledygook like that. Um, An example of a rate like this would be the unemployment rate in economics. So it's the portion of the labor force that is seeking work but does not have a job at the moment. Um, Incidentally, if you ever have this kind of chart or graph in a presentation, first of all, make sure that the numbers add up to 100. The last thing you want during a presentation is having a mistake in the arithmetic, because you'll lose all credibility. The second thing, make sure that you know what this is a proportion of. In this case, is it weight by volume? Doesn't state any of this here. So make sure that if you have a chart that it's clear to your own, in yourself anyway, what the various numbers of the graph represents. Now let's take a look at rate as change. And this typically involves time. And in this sense, we're looking at, if you think of it, distance tells you where you are at a given moment, but speed tells you how fast you're moving away or moving towards something. In the same sense, you can talk about speed as you move, but then acceleration would be explaining how your speed is changing. Furthermore, this idea of change, you can imagine this as arithmetic growth, for example, where you're just adding the same number each time, whereas exponential growth means you're adding a certain percentage. And so as a result, the growth is going to be increasing because there's increase on the increase. Uh, uh, Furthermore, if you've ever had trouble doing calculations of rate of increase or decrease, this simple little formula will almost always work. If you've learned another way to do it in secondary school, that's great, whatever works, but this will typically work for almost all occasions when you're looking at a rate as some kind of change. So it's the new number minus the old number divided by the old number. Let's take an example here. I've got the consumer price index, which is a measure of the cost of a basket of goods of a typical consumer. I've got the number in 2019, which is 136.4. I got the number for 2018. So you can sort of imagine that a basket of goods might have cost $136.40 in 2019. The year previously, it was 133.4. So to calculate the percentage increase, this is inflation, you take the new number minus the old number divided by the old number, do it with a calculator. You can report it either as a decimal, as we learned before, or as a percentage. Both numbers are identical. Another example of something like this would be the birth rate and death rate. Once again, the difference between the two would be the net increase in population. This is ignoring immigration. But then there's other examples where you might think of it as a rate of change, but in actual fact, it's like a proportion. And finally, mathematically, they're the same. But the fertility rate is number of live births, for example, by the women between the ages of 15 and 49 times 1,000. Infant mortality rates are another example. You might think of them as a rate of change, but not really. It's still a proportion. I want to take a quick glance at this idea of different types of rates, and you'll notice how they're written. Okay, the symbols used. As we know, a percentage is with zero, a little zero with a slash and a zero. For example, as a proportion, 11. This is roughly true around the world, men and women, and different nationalities, it's about 11% of the population is left-handed, which means 89% are right-handed. Of course, there's people that are ambidextrous that can write with both hands, use both hands. And then rate as change, typically it's annual interest, which, for example, 5% means $5 per $100 per year, if we're talking the annual interest rate. Then you'll notice some rates are indicated per thousand. A moment ago, I mentioned birth rates and death rates. You'll see that then it's written with two little zeros at the bottom. And the reason birth rates and death rates are typically written this way so that the number looks a little bit larger. So it's per thousand in that case. There's even, this is rare, but I've seen it, per 10,000 where they put three little zeros. Hospital beds, traffic deaths. I have heard basis points. This is used for in finance. They're talking about the two decimal places after a percentage, and in effect, it's per 10,000. Per 100,000, I've never seen this, but apparently the number of medical doctors per 100,000 population is a statistic. The last three are the ones that I really want to look at because these ones you'll see frequently in news reports. ppm is parts per million, and I gave an example of what that is: one drop of water in a gas tank. So it's a quite small indication. Parts per billion. This is minuscule, and it's written as ppb. Finally, I've heard even things like parts per trillion, which is, I don't know if you've ever been to the Olympic Stadium, but the Olympic-sized swimming pool there, imagine it 20 times, and you go up one drop of water. And I think any reports of parts per trillion are probably more an indication of the ability of the test to be able to detect minute quantities in an area. Even parts per billion, you'll sometimes read about a toxic chemical that's at parts per billion, and I frankly wouldn't worry too much about it, because unless it's something extremely toxic. Lastly, I want to take a look at this idea of different shapes of graphs, and we'll be looking at this in the course later, but I first want to start with a shape that might be considered as symmetrical. So I'll just do this like this. Here we've got a shape that's symmetrical. And it's symmetrical because if, for example, I put a mirror down the middle like this, it would look the same on both sides. This is the famous so-called bell curve, or a Gaussian distribution, or a normal curve. They all mean the same thing, but the shape is like a bell. This is symmetrical. Just as a quick point here, because we'll be talking about this later, is that you can imagine this as being the center. So this is a measure of the center here. And then this is telling us how spread out the numbers are. So for example, if I were to draw this a little bit differently, let me do it like this. I'll get rid of this one here too, and draw it here like this. It would still be a bell curve, still have that same shape, but you can see that it's not so wide anymore. So it's not so spread out. A uniform distribution is like this, like, for example, and like that. So that means to say it's the same everywhere. Here, it's not the same. It's symmetrical. A uniform distribution is both uniform and symmetrical. Once again, if I put a mirror down the middle here like this, then you can see, if you put a mirror, you'd look on it both sides, it's the same. That's the definition of symmetrical. Uniform means that it's the same everywhere. This is clearly not uniform, but it is symmetrical. This is both uniform and symmetrical. Skewed, finally, there's two that I want to consider here. Let me consider a graph that's shaped like this. So it's sort of like a bell curve, except in this case, there's like a tail on this side. So we can talk about the spread, we can talk about the center. The center would be somewhere around here, but you'll notice there's a tail. And I often say that if it's a dinosaur, the tail is on the right, so we say this is right skewed, because the tail is on the right, which is also sometimes considered a positive skew. If, on the other hand, I were to draw another graph over here that would look like this, then we'd say the skew is on the left-hand side, so it's known as left skewed, and that's also known as a negative skew. So if the dinosaur's tail is on the left, then we say it's left skewed or negative skew. If the tail is on the right-hand side, we say it's right skewed or positive skew. This graph I've shown here, it's uniform. It's not skewed. This is not skewed. Well, my drawing isn't that good, but there's no skew to it. That's the idea.